Chapter 10 deals with bonding and properties of solutions and solids. So let's talk about the nature of chemical bonds to begin with. We'll start with covalent bonds. Covalent bonds are formed when electrons between two atoms interact with another atom's nucleus. In this case, we've got two atoms right here in their nucleus, and we can see that the electrons associated with each atom gets trapped between those two nuclei. That results in a much stronger interaction because the electrons are stuck basically between these two atoms. Now, the bond strength of this, or the degree at which the electrons are held in place, is dependent upon the attractions of the electrons to the nucleus, but is also affected by the repulsive forces of the electrons from each other, as well as the repulsive force of the two atoms' nuclei. When we talk about molecules and structures, we have a way of representing molecules in two-dimensional space on paper using what's known as a Lewis structure. Lewis structures are two-dimensional representation of three-dimensional molecules. And what we find is that when we draw Lewis structures, we draw the connection between atoms using lines, and then we represent other electrons with dots. So we need to be able to draw Lewis structures here. So the first thing we need to do is we need to figure out how many valence electrons there are in each atom. And that is, how many electrons do we have in the outermost shell of the atom? So we have to total the valence electrons of each atom. So in this case with PCl3, we've got 5 valence electrons from phosphorus, and we've got 7 valence electrons for each chlorine, and then we've got 3 chlorine, meaning we've got 26 electrons total we have to deal with. Since this isn't an ion, that's the only electrons we have to worry about. If we had an anion, we would add more electrons to this total. And if we had a cation, we would subtract the charge, or the charge from the total electrons. Now, in order to figure out how to draw this particular molecule, we need to figure out what the least electronegative element is. And the least electronegative element is going to be the central atom in our structure. So when we try and figure out what's the least electronegative element, we have to remember that electronegativity is the ability of an atom in a molecule to attract an electron to itself. On the periodic table, electronegativity increases as you move from left to right, as well as from the bottom to the top. And when looking at electronegativity, if you remember, fluorine's the most electronegative element, and cesium's the least electronegative element, there really isn't any exception to this trend of increasing as you move up and from left to right. Seeing that phosphorus is less electronegative than chlorine, then what we do is we draw phosphorus as our central atom. Now, every atom is trying to be like a noble gas. That is, it wants to have 8 valence electrons surrounding it. So what we do is we first tie the atoms together using bonds. So the phosphorus is connected to the 3 chlorine atoms by drawing a single line between them. Each line represents 2 electrons, so we've used 6 electrons so far. And then what we do is we put the remaining electrons, out of our 26, we've used 6 as bonds. The other 20 we're going to assign to the chlorines, making sure that each chlorine atom has 8 electrons around it. Now, when we put electrons around atoms, we put them in groups of 2, and you can see we've got 2, 4, 6 electrons around the chlorine plus the 2 electrons in the bond. So that means this chlorine now thinks it has 8 electrons around it, and it does. In fact, all 3 chlorines have 8 electrons around it, but we had a grand total of 26 electrons, and so far we've only used 24. So we would put the remaining 2 electrons on the central atom. So when assigning electrons after bonds are placed, the most electronegative element gets electrons first, and then the least electronegative element gets the remaining electrons last. And if you run out of electrons before the central atom has completed its octet, then what you need to do is you need to take electrons in the form of lone pairs, that is those sets of 2 dots, and change them into a bond. So for every line, you have 2 dots. So you can see here, the nitrogen over on the left, on the bottom left, takes 2 of its lone pairs, sets of 2, and turns what was once a single bond into a triple bond here. It's not enough just to have a Lewis structure. We also have to figure out if the Lewis structure is correct. And we find if our Lewis structure is correct by calculating something known as formal charge. Formal charge is the charge an atom has while it's in a molecular compound. And what we try and find or do is that we look for a structure where the formal charge is 0 on the greatest number of atoms. The way we figure out the formal charge is by taking the number of valence electrons that an atom normally has. So in carbon dioxide, for example, here we've got carbon with 4 valence electrons. And you can see in both structures of CO2 that it's surrounded by 4 bonds. And so when we calculate formal charge, we calculate the formal charge based off valence electrons, the number of bonds something has, and the number of remaining electrons in the form of dots. In both cases, carbon has 4 valence electrons, it has 4 bonds, and so in both structures there is no formal charge on carbon. That is, it's equal to 0. If, however, we look at the oxygen over on the left structure, where there's 2 bonds between carbon and oxygen, we can see that oxygen normally has 6 valence electrons. And what we find is that if we take our 2 bonds plus our 4 electrons here, well, 2 plus 4 is 6. 6 valence electrons minus 6 from the 2 bonds and 4 electrons, we get a formal charge of 0 on both oxygens on the left structure. On the right structure, we see we don't. We see we actually have atoms with formal charges other than 0, which is not an ideal situation. So when we go to pick the Lewis structure, we always have to calculate the formal charge, because if we want to know if our Lewis structure is correct, our Lewis structure will be the one with the fewest formal charges on it. And if we do have to have a formal charge on something, then the negative charge will end up on the most electronegative element. So of the 3 Lewis structures shown here, number 3 is the correct one because oxygen is the most electronegative of the 3. It's best equipped at having an extra electron associated with it.